Welcome everyone. For today's prep, we're going to keep going with chain rule. So again, this is one of our special derivative rules and probably the one we're going to use the most. So I really want to take some time with this. And we're going to look at it for two special cases. And let's get started. And we're going to start with example 2 again. We looked at this last time. We're going to look at it again. And what we're doing here is we're writing each function as a composite function composed of two simpler functions. So we're trying to break our function apart into its two simpler functions. And we did this in part 1, we did it for this power function. And here we identified that the power function was on the outside. So we called that raised to the power 8 our outer function. And then all that stuff that was inside the parentheses there, we called that our inner function. And then in class, we did the same game for the sine function. So we had sine, and then we had parentheses, and then all that stuff. So in this case, the outer function was the sine function. And then again, all that stuff was inside the sine function, so we called that our inner function. So we're going to do the same thing, but now we're going to do it with e, an exponential, natural exponential, and our natural log function. So again, let's look at this exponential. Actually, let's start with the natural log here. I think this one's easier because we have that nice set of parentheses. It's always easier to pick out what the inner function is when you see the parentheses. And when we look at this, we have that x to the 4th plus 9x plus 3, all inside the parentheses there. And then our natural log function is kind of outside of that. So for this one, if we're going to break this apart, we're going to call the natural log function our outer function. And the inner function is going to be, well, the kind of the same thing it's been, this x to the 4th plus 9x plus 3. So we're just kind of breaking this apart into the outer function and the inner function. And here, the x to the 4th plus 9x plus 3 is literally all the stuff that's inside the parentheses. So it's the inner function. Now for exponential function, we don't normally write this, but I think it can be helpful. You can think of the exponential function here, and a lot of like Excel uses this. Some different programming languages use this. So a way to write the exponential function, we don't normally write this by hand, but a way to indicate the exponential function is with this exp. And we take all the stuff that's in the exponent, and essentially what we're doing is we're plugging it into this exp function, so the exponential function. So again, we don't normally write it like this. I know Excel kind of uses something like this, and some other languages. So this does exist. But when we're looking at this, we want to think of the exponential function, as our outer, and then all that stuff that's inside the exponent, that's our inner function. It's inside the exponent. And if we have it written like this, it's just a little more obvious. So again, this isn't normally how we write it. We won't be writing this in class. But it's a way to think of it. So for our case, if we're going to write this as an outer function, we want our exponential function. So e to the x. And then our inner function here is going to be all the stuff that's inside the exponent. So the x to the 4th plus 9x plus 3. So again, we're just breaking this up into our outer function and our inner function. And this is just a way to kind of think of it. All right, so we want to be able to differentiate things like both of these. And what we've seen with the chain rule, so let's go back to our chain rule. What our chain rule says is, in order to differentiate a composite function like this, we start by differentiating the outer function. We keep our original inner function exactly the same, and then we multiply by the derivative of the inner function. So the chain rule kind of gives us a way to break through all the different layers of our function. And we're going to look at this for the special case. I get to it here. We're going to do this for the special case when our outer function is an exponential. So we want to differentiate something like the function we just worked with. So the derivative of e to the ux. So again, the outer function is that exponential, and our inner function is whatever's in the exponent. And so when we differentiate the exponential function, the derivative of the exponential function is nice. It stays exactly the same. So that's what we're seeing here. It's the derivative of our outer function with the original inner function plugged in. Doesn't look like anything happened, and that's because the derivative of e to the x is just e to the x. So the derivative of our outer function is exactly the same, and then we keep the same exponent. And then we multiply by the derivative of the inner function, so the derivative of the exponent. So this is really just a special case again, where the outer function is an exponential, and the inner function can be just any general function. So let's see how this looks for that function we are working with. So this e to the e raised to the x to the fourth plus 9x plus 3. Let's calculate the derivative. So when we differentiate, our function's called h, so we'll call our derivative h prime. And when we differentiate an exponential function like this, the exponential part stays exactly the same. So we're going to have the exact same function reappear here. E to the e raised to the x to the fourth plus 9x plus 3. And then we take the term that was in the exponent, our inner function, and we're going to multiply by its derivative. And so when we finish this off, again, this exponential part we're done with, so that doesn't change. And then the derivative of the term here, if we do some power rule, 4x cubed plus 9. And we need the parentheses here because everything has to get multiplied. And that's really it. That's our chain rule for the exponential function. So when we differentiate an exponential function like this where we have a complicated exponent, the exponential part just stays exactly the same, so you don't make any changes to it. And then you just multiply by the derivative of the exponent term. All right, so let's look at our log function. So what happens when our outer function is the natural log? Well, again, let's kind of look at this. So we're going to look at the case where the outer function is natural log, and then we just have some general function u of x for our inner function. And so it helps to remember that if we were to differentiate just the natural log function, the derivative of that would be 1 over x. So what we're seeing is, so a way to kind of think of this is when we differentiate natural log x, we kind of get the reciprocal of whatever was inside the natural log function. So the way the derivative for natural log for u of x works is we're going to take all that stuff that's inside and we're going to do the reciprocal. So this is essentially the derivative of the natural log part, and we're keeping the inner function exactly the same. So again, when we differentiate the natural log part of this composite, it's almost like we're taking all that stuff that is inside and we're getting the reciprocal here. And this part is the derivative of the natural log. So we've broken our way through, and then we multiply by the derivative of our inner function. And again, this is just a special case for when our outer function is the natural log, or really any log function, but this is written for specifically for natural log. So let's try an example, the one we just looked at. So again, our function here is called h, so we'll call our derivative h prime. And when we start, again, this is a composite function, so we have natural log and then all this stuff inside. So the way this chain rule works for log functions, when the log function is the outer function, we're going to take all that stuff that's inside and we're going to do the reciprocal. So we're going to get 1 over x to the 4th plus 9x plus 3. So we just do the reciprocal of all that stuff. This is essentially the derivative of the natural log part. So derivative of natural log gives us the reciprocal of whatever's inside. And then once we work our way through that log function, we're going to take all that stuff that's from inside and we're going to multiply by its derivative. So derivative of this x to the 4th plus 9x plus 3. And then we finish that off. So we have our fraction. And again, we need parentheses here. And if we leave it like this, we do need the parentheses. But if we want, we can take this 4x cubed plus 9 and move it into the numerator. And then we don't need the parentheses anymore. So either of those is fine. And that's it. So what we're going to see in class is, well, kind of where the chain rule gets its name, because you can kind of keep repeating this. And we'll see a couple examples where we might have to use the chain rule more than once. So there's kind of like multiple links in our chain. All right, so we'll stop there, and then we'll see you in class. Bye-bye.